Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and today I'm joined by Eve.
Hi.
Eve, do you want to say a bit about where you're calling from, what you're up
Yes,
to, what we're doing today?
I'm calling from my parents' attic in Sheffield. I'm a PhD student in Sheffield. I do some outreach in Cambridge as well. And yeah, we're going to talk about some counting.
We could do some counting. Happy Pi Day, everybody watching. Sadly not Pi themed, but let's find out how people's day is going today, given that it's Pi Day. We always do a poll at the start to find out how people's day is on a scale from 1 to 5, where voting for 3 would, I think, be a little bit funny because of Pi. Should always explain my jokes. That's how I make sure that they're extra funny. Eve, how's your day been on a scale from 1 to 5?
Oh, I'm on a 4, I think. I'm not very well, but I've been looking forward to this. So.
Oh, sorry to hear that. Yeah, I've been looking forward to this one as well. People in chat are having a pretty good day so far. Let's let people vote and see who we've got in chat. Who can I see? I can see Akshay, Andre, some anonymous people. Aya's here, Miles, and Herb and E. I can see, yep, someone's done my joke. They say they can't vote for 3.14, so they'll vote for 5, which is the closest to 2 pi tau. Quick plugs at the start, things that I want to mention. Open days, we're doing these in about a month. For a while, technical issue, for a while this link that I've had on screen every week for the last few weeks, for a while that link was broken. So I'm really sorry if anybody typed out the link from the live stream and then it was just broken and you couldn't book onto the open day. We've fixed it now, I think. So if you want to book onto the open day to come and see us in April in Oxford, that's a thing. Jane Street have released a new puzzle. So we're stream supported by Jane Street as well as the Maths Institute at Oxford. Jane Street make puzzles. I mean, they do a lot of different things, but the most recent puzzle is about drawing hook shapes onto a grid. You're given some clues. It's like one of those puzzles you might see next to the Sudoku or something. You have to draw L shapes, and there's rules about how the numbers interact with the shapes and positions of the L's that you draw. So if you want to see that, you can head over to Jane Street Puzzles. They've got lots of previous puzzles. Most of them are too hard for me. So if you want a challenge, Jane Street has got some of those. My students are in chat and they have just said Happy Pi Day. So Happy Pi Day, all of the new college students. Eve, you sent me this ad. Do you want to say anything about this event?
I mean, I'm tempted to just let it speak for itself. No, I'll say some things. So I run a summer school at Mary Edwards College for people who are interested in taking STEP and want some help preparing for it. It's only open to women. I'm going to say that before people get excited about being able to apply. And we're opening applications in a week. So if that's something you might be interested in, then there's a link. I'm not sure if you're going to be able to.
Oh, I've got the link. Hang on. I can put the link in chat.
That could go in chat. That's probably the best way.
Link in chat. I almost prepared this perfectly, but then also forgot. It's the classic dichotomy of having it in a notepad file, but then not quite copying it live.
So yeah, it's just 4 days of maths geared towards preparing for STEP.
Nice. And you're in charge, you're kind of lead tutor for that, or lead, what's your...
Yeah, I kind of run around trying to do everything very quickly.
Aided by a team of other people.
Aided by a team of other people who are teaching in a more calm manner.
Yeah. People in chat say Eve's mic's a little bit quiet. I'm going to fix the gain a little bit. Let me know if I've made that much better or much worse. Okay. That's an instruction to chat, I think. It's the sort of thing that neither
you probably
Eve nor...
need to say things for them to be able to do anything with it, though, right?
Maybe. It's the sort of thing that neither Eve nor I can tell how loud anything is. Are there any eligibility criteria? I think it's looking for people studying maths and further maths at A level.
Yeah, you need to be doing maths and further maths. That doesn't mean you have to be doing further maths this year. If you are at a place that does maths and then does further maths, that's fine.
On track.
And you need to be interested in applying for somewhere that requires STEP. So on a needs basis rather than a this would be fun basis.
But it would also be fun. Maybe that's me undermining the eligibility.
It would also be fun, yes, but you need to require it and also find it fun to be allowed to apply. Yeah.
I find this really exciting because many years ago I used to work on a STEPS summer school in Cambridge when I was a student. I don't know if you did as well, if you were involved in.
No, I'm slightly too young to have worked on
But then there's sort of follow-up STEP things, and this is STEP support has evolved and done different things at different times.
Yeah.
Well, there you go. Okay, people say we fixed the sound, so that's a good start.
Excellent.
Okay, right, good. Okay, I think we're here. Oh, how many people go on the summer school? Is it a big thing or a small thing? Or?
This year, I think it's up to 50.
Okay. So.
Yeah, the answer varies depending on how much money we have.
Okay, right. Funding dependent. If lots of people apply, is that helpful?
It's really helpful if more than 50 apply, but we usually manage to achieve that without too many problems.
Okay.
If like 400 people applied, I have made a case before to expand numbers successfully, but by 10 rather than by 100.
Okay. So if you're watching and you're interested, here's a thing. Right, good. Okay. Yeah, okay. If you're halfway between maths and further maths and you're pretty sure you're going to be doing further maths, and you attend the summer school, let's say, and then it turns out that you weren't doing further maths, nobody's going to come and try and remove the knowledge from you. So in some senses, there's an intention there, I think, if you're intending to do further maths, which no one can really scientifically measure. Right, let's move on from the nature of time and causality. Story maths. Over to you, Eve, I think.
Yeah, so I wanted to talk about this because quite often when we show equations hold, we kind of start with something that we know is true, and then we do some manipulations until one side looks like the thing we're aiming to show our equality for. And that's all well and good, but I really like proofs that instead of doing this kind of manipulation, kind of look at each side and go, okay, can I come up with a story that says kind of this side measures this thing, and now I can measure it in a different way, and that's the story being told by this other side, so they have to be equal to each other. So that's going to be the idea of today. I think it would be best if we did an example first, because I think that's very nebulous if we don't have a concrete example to weigh it down with. So before we jump in, I want to remind everybody what a binomial coefficient is. So the binomial coefficient n choose r is going to be the number of ways of choosing r objects out of a collection of n. Just wait for them.
Yeah, my writing is going to be slower than choose r from n. And I think some people write it ncr. Are we going with the stacked things inside brackets today?
I'd like to write it as stacked things inside brackets, but yes, people may be more familiar, especially if they've got it on calculators, with ncr. So as a kind of very first example of that, if I have a fruit bowl and it's got a banana, an apple, an orange, a pear and a strawberry in it, and I want to choose 2 fruits to have for my lunch, the number of options I have for that is 5 choose 2. And you can calculate that, it gives you 10. Oh, thank you. Here is my fruit bowl.
Yeah, I know, look. It's like we prepared the first bit.
I know.
So you say calculate that. People at A level, I think, learn a formula for this thing, but also you
They do, yeah. We're going to get onto the formula in a little bit. So, in fact, immediately. So you see a formula for this, which is that n choose r can be written as n factorial divided through by n minus r factorial.
Factorial as well? Oh, I'm getting confused about C's and R's. Do I want an r factorial here?
R factorial. Yeah. Great. And I don't want to prove this now, but this is a really good thing to prove using a story proof. So maybe after this live stream, people could have a go at proving that using a story proof. You can prove it by induction, but I think the story proof is more satisfying.
Okay.
So yeah, kind of the first thing that we can prove using these story proofs is that Pascal's identity, which says that is that Pascal's identity? I get all my identities mixed up. I'm going to prove that n choose k is the same as n choose n minus k. I think Pascal's identity is not that.
Okay, but this is a. I think
That's
this
what
is
I'm
a
gonna
true
put.
fact. So that we'll put like
Yeah.
claim or something here
Yeah.
for what you're claiming. That
Yeah.
I suppose.
And
Okay.
to kind of give you an idea of how this proof's going to go, I think I sent you some pictures of ways of picking pairs of fruit.
Oh yeah, shall I put those in?
That would be great. Yeah.
Is it the file called pairs of fruit, but you've
Yeah,
spelt
with
it?
pairs spelled P.
Yeah.
I'm glad you noticed that. Yeah.
No. Yeah, okay, it's spelled. Yeah.
Yeah. Um. So, yeah, this is kind of representing the 5 choose 2 being 10 because I've got 10 pairs out of my fruit bowl. And what I'm going to do is kind of think of ways of choosing a pair of fruits out of these 5 and thinking, can I turn that into a way of choosing 3 fruits? So, is there any way that a banana and an apple is related to a choice of 3 fruits? Maybe some of them are banana or an apple, maybe none of them are.
Is that a question? Should we get chat involved?
We can get the chat. I think that would be good.
Okay, so you've got all of the ways of choosing 2 things, and I guess the claim is there are just as many ways of choosing 3 things.
Yeah.
The challenge is to find some sort of way of matching them up to.
Matching them up, yeah, exactly.
Okay,
Yeah.
so for example, to pair this choice with a choice of 3 things from the kind of the image I don't have of the 10 choices of 3 things, what's the sensible kind of order to display them in, I guess.
Yeah.
Let's see what chat thinks. We'll let chat run for a little bit. If you want to join chat, we're at slido.com/OOMC, and you can type in there. You can be anonymous if you want to, which some people are choosing to do, and you can tell us a story about why choices of 2 things are the same number as choices of 3 things if you've got 5 things total. Okay, so Eve can't see chat. I can see chat. Chat's saying things like, if you pick 2, there are 3 you didn't pick. All the fruits that aren't bananas or apples in this case is 3 things. Okay, Eve's not.
They're not, yeah. So that's our very first example is I can say n choose k counts the number of ways of choosing k things out of n. But that would be the same as choosing n minus k things to not pick. So these 2 things both do the same job, just in a slightly different way. My procedure for the first one is choosing what to pick. My procedure for the second one is choosing what to not pick. Exactly.
Yeah, thanks to people in chat as well. And I like that this proof doesn't rely on knowledge of what the formula is. That you could go and plug stuff in. But, yeah.
We're basically, we're going to ignore the formula the whole way through. We're just going to use this definition. But you can prove the formula like this if you're interested in doing that. Okay, let's do another example. You can prove the binomial theorem this way, sort of.
Okay, which one's the binomial theorem?
I'd like n to be a positive integer, please.
Okay.
And I would like to say that x plus y to the power of n can be written as the sum from, k is a good letter, let's stick with that, from k is 0 up to n.
Okay. Now what do I put here? It's like x to the k, y to the n minus k, and there's a coefficient at the front. The coefficient is the binomial coefficient, n choose k.
Exactly. I'm actually going to claim a little bit more than that. I'm also going to claim that each n choose k appears in Pascal's triangle in the way that people are used to looking it up in Pascal's triangle. So n choose 0, n choose 1, and so on, n choose n is the n plus 1th row of Pascal's triangle.
Okay. So these things are going to be the things that appear from k is 0 to n? Is that what you're saying? The coefficients are going to be?
Yeah. And yeah, I think the fact that they appear in Pascal's triangle isn't really the statement of the binomial theorem, but because it's kind of taught in schools in that way as a way of looking them up, I wanted to bundle it all up together.
Okay.
So if we look at a kind of way of thinking about this, if we wanted to expand that bracket without knowing the binomial theorem, what we would do was we would put x plus y next to itself n times, right?
Oof. Yep. I'll try and visualize that. Carry on.
And then we'd multiply those brackets out and we'd add up loads of terms, right? So individually, we're going to get some x's multiplied together and some y's multiplied together with a coefficient of 1. And then we're going to have to worry about adding them all up. And because there's n brackets, our powers are going to have to add up to n. So we might want to think about, well, how many terms are we going to get that look like x to the power of k times y to the power of n minus k?
Sure, okay. So this is imagining doing all the algebra to multiply things out. Chat says, I think this is great, that it's not obvious that the numbers in Pascal's triangle, you have some ideas about how they work, about adding up smaller numbers. That's not obvious from what we've said so far about, it's not obviously related to choosing, and it's not obviously related to the formula. We're trying
Exactly, that's where we're going.
That's where we're going, okay.
Exactly that's what we're trying to do, yeah.
Aha, okay, right. I see, so you're going to, this is going to end up proving that this is exactly related to your ideas about Pascal's triangle. Okay. So what do I think happens? When you multiply out all these brackets, you get x to the n one time, from if you pick all the x's from the brackets.
Pick all the x's, yeah.
Okay. You get x to the n minus 1 times y quite a lot of times. I'm looking at things like you pick all the x's and then in a kind of first outside, inside, last way, for the very last bracket, you pick the y instead. That's like a outside kind of term.
Yeah.
But also a bunch more of y times x to the n minus 1. So where are we going with this?
So we kind of keep doing that. We're kind of saying, well, if I have x to the power of k, x has to have been in k of those brackets to begin with, right?
Okay.
And the other brackets have got to have a power of, they've got to have a y picked from those.
I see. So you're kind of choosing k of the brackets.
Yeah.
Choose k of the brackets, and that corresponds to the coefficient of x to the k.
Yeah, I'm declaring that I'm taking an x from that one.
Okay, I should not write down the whole story because it's too much writing.
No, yeah, that would be
x from that one. But that does, I think that does give me from those ones, I guess. I'm going to stop writing.
Yeah, so that should tell you that there are n choose k ways of arriving with x as your to the power of k, right?
Okay, that convinces me that the coefficients that turn up here are something to do with the number of ways to choose, but not yet. I think that it's something to do with Pascal's triangle. Or
we haven't started on Pascal's triangle.
We haven't started. Okay, separate claim. Okay.
Yeah. So this is really going to be two proofs. Like they're not. I've just done.
I got really distracted by Pascal's triangle, one of my favourite.
Yeah, I got the sense that was happening. Maybe I should have saved that till like.
Well, show me the triangle. Okay. Sorry.
No. Yeah, I'm going to deliberately not show you the triangle for a little while. Instead, I'm going to show you a grid.
Okay.
And this is the bit where I asked for your amateur drawing of a snail.
I've got to draw a snail. Okay.
Yeah.
Regulars on the stream know that this is actually a professional art stream, and the thing that I'm really best at in life is drawing. Wait, how do snails work? They've got little bits here, and they've got little tails. There we go. Okay.
Beautiful.
Okay. Why did I draw a snail?
I'm gonna get this. I'm gonna tell the story using the snail.
Okay.
So I'd like the snail to have the option of moving around on a grid.
Okay.
Yeah, maybe let's pretend it's an infinite grid.
Ooh, okay.
We're always going to use it finitely, so it's not going to be a problem. Yeah. When I say an infinite grid, sorry, that was really ambiguous. With a bottom left corner, so only infinite going right and going up. Yeah.
Okay, it's going that way and that way.
So I'm going to think about the ways this snail can move. So I want you to imagine it kind of leaving a snail trail behind it, which is why it's a snail. And I'm going to say it's quite slow, so it can only move 1 unit at a time. And it's also not very good at directions, so it can only move to the right or move up. It gets really confused if you ask it to move down or left.
Okay, so it's just
Oh
going
wow,
to
we've got a mobile snail.
I
That's
can move
great.
it around. Yeah, yeah, yeah. Professional
And
live stream.
I'd like us to just spend a little while thinking about the number of ways for that snail to move to the point um, with coordinate 3, 2, which I think is on your grid.
Okay, okay. Let me circle that. It's going to 3, 2. I remember coordinates. That's this one over here.
Yeah.
Okay, so snail's going to get there, but it can only go right or up, and only one square at a time.
Yeah.
Like the number of routes that it could take, number of snail trails that it could draw. I guess.
Probably let chat think about that.
Yeah, I will let chat think about that. I'm also going to use the time to draw like a little snail house where it lives down here.
Excellent.
Okay, chat. There's a snail at the bottom left. It's got to move 3 squares right and 2 squares up to get to 3, 2. But it doesn't have to do. Yeah, you do some. It's got to get to the point 3, 2. Because over there is a lovely cabbage. Lovely. A suggestion in chat: right, up, which is actually the cheat codes to unlock bonus content on the Maths Club. Sorry, no, it's how to get to Snail. Right, it goes right, or she goes, and then up to get to the cabbage. Great, you've successfully navigated. Snail getting to cabbage. Aya guesses 6. Neutrino says 5. No, wait. In any, there's people in chat saying in any order. So the cheat code that someone gave me before. Somebody else has said right up, and what that's got in common is that it's 5 things with 3 R's and 2 U's.
So the really important thing going on here is that you need to step right 3 times and you need to step up twice, right? That's how you go from 0,
right,
0.
Okay. So the roots. Well, how am I going to draw the roots? I'll start drawing the roots while you talk. Sorry.
So each of these roots that's kind of being mentioned that works, overall we're going to go right 3 times and we're going to go up twice, because that will eventually end up in having gone right by 3 and up by 2, which is what we want to end up doing. What doesn't matter though is the order that we then do these things, right? We could, if we go up and then right, that will take us eventually to the same place as if we went right, then up, then up. The order's really not going to matter. So there's kind of quite a few ways of doing these, James's.
I'm trying to draw them. People in chat seem convinced that it's 5 choose 2, which is 10. I've only found 6.
Yeah, conveniently we computed 5 choose 2 earlier, right? So we've got some steps. We've got 5 of them. We've got 3 rights and 2 ups. I usually draw these as just space holders next to each other.
Oh, I see. Right, like you're going to give the snail some little route map directions of how to get to the cabbage.
Yeah, and I'm telling the snail kind of, I need you to go right 3 times, and I need you to go up twice, and as long as you do that, I don't mind. And so the snail can just pick 3 of these to be a right step, or it can choose 2 of them to be an up step. There's another proof that 5 choose 3 is 5 choose 2. Kind of the same proof, but. And as long as the snail does that, then we're going to get a route. And in order to have done 3 right steps and 2 up steps, we're going to have to have done them in some order. So all the ways is going to be given by 5 choose 3.
See, so that you've reduced the problem about finding all these routes to thinking about the instructions, and that's a simpler problem of thinking about the permutations of these instructions. Let's try permuting the instructions a little bit more.
Exactly.
Okay. So then that will be. It's got 2 ups and 3 rights, and it'll be right, up, right. Somebody gave me that one in chat. There it is, right there. I'm missing right, up, right, and up, right. Yeah, my pictures on the right are not going very well. Also because I've done them way too large. I didn't leave space for 10 of them.
Yeah, no, you're not going to have space. But
I'm going to pretend I didn't try.
So that's a kind of nice way to see that we can get n choose k kind of, we can imagine putting um, a 5 choose 2 on that space representing the number of ways that the snail can get to that part. And we could do this for the whole grid, right? We could label each corner with the number of ways the snail can use to get to that.
Right, so this is 4 choose 1 because it's got to go 3 plus 1 bits of moving, one of which is up.
Yeah.
Whereas this is 4 choose 2 because it's 4 bits of moving, 2 of which are up. This is 4 choose 3. You can kind of do lots of different versions of this problem once you've had the idea. I guess this is 3 choose 0.
Yeah.
None of them are up. 3 choose 1, 3 choose 2, 3 choose 3. Okay, I can fill in the rest of these, I think.
Yeah. So the super fuzzy version I have of chat is going on quite a bit, but I don't know if people have got observations about this.
Oh, if the snail can move in 4 directions, they're trying to extend it. Unfortunately, if the snail can move in 4 directions, then you need to allow for the mischievous snail who gets in here and starts doing sort of donuts around and around and around. I think it becomes infinitely many if the snail's allowed to do some number of loops along the way.
Yeah.
Sort of.
So, and I can also kind of think about how these numbers are going to relate to each other, right?
Yeah.
So if I think about my snail getting to the cabbage, there aren't that many places it can have come from.
Yeah, if it's only allowed to go right and up. Okay.
Yeah, so the place it would have been at its last step are either one to the left of where it is now or one below where it is now, right?
Right, it either came in from here or from here.
So that kind of gives us a link between how these numbers work, right? To get the number at the cabbage, I have to add up the number to its left and the number to the bottom. Because every path I have is either one of those paths to the left with a right step added on, or it's one of the ones underneath it with an up step added on.
Okay, the number of ways to get to the cabbage is the number of ways to get to this sunflower plus the number of ways to get to this windmill.
Yeah, exactly.
Either you visited the sunflower or the windmill on your way to the cabbage, not both, and then you could go to the cabbage.
Yeah. So we know that we can kind of relate all these grid squares by saying, okay, I get each one by adding up the things to my left or underneath me. And if you kind of tilt your head.
Ooh.
I don't know if you can rotate.
This is what people mean when they say look at the problem from another angle, right?
Look at the problem from another angle, exactly, yeah. This gives you Pascal's triangle.
Pascal's triangle that way around. Wait, I can save everyone at home, I think. Hang on.
Yeah, you have to really tilt your head. You have to.
Wait, it's a computer, we can fix this. Okay. So it's Pascal's triangle. Oh, like this way around?
Yeah.
Behold, Pascal's triangle.
Because our addition rule is working the way that we know for Pascal's triangle.
Right.
And we start with a 1 at the top.
You do start, there is one way for the snail to stay stationary. Or if you prefer, there is one way for it to get to here, and there's one way for it to get to here. I should point with this pen. One way for it to get here, and one way for it to get here. Which is like, if some people start Pascal's triangle with a pair of 1s, and some people start with a single 1.
Let's do these. Yeah.
So this story about the windmill and the sunflower and how do you get to the cabbage is, in some sense, a story about relating together different binomial coefficients, different choosing things. Yeah. And then if you turn your head sideways or rotate the picture, it's a story about Pascal's triangle, and it shows that those things are all the same. We haven't invoked the formula yet, and I think that's powerful. That if you wrote out the kind of general thing, n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1, I think it'd be really tempting to try and just sort of bash that out with the formula and your knowledge of factorial functions, which works. It's just not as fun.
It's not as fun, and often there's a reason for going back to develop new ways of proving things, right? So a bunch of other things that are, much more difficult to show. It's possible to come up with a story proof as to why they work, but mangling algebra wouldn't be track. We might not even have algebra available to us in these kind of situations.
Yeah,
So,
you're kind of lucky in school to know a formula for the binomial coefficients.
yeah.
You might only know these kind of relationships between them. Anonymous in chat does the thing. I was wondering if anybody does this to start the Pascal's triangle with a single 1 at the top. One person does that. Yeah, the number of ways should be, yes, if you're using xy coordinates, I agree, it's x plus y factorial divided by x factorial, y factorial. Andre, that is the sort of formula I was trying to think of in my head when you saw me slowly writing all the numbers in to try and spot the pattern to make sure I was getting them all right. But yeah, once you've rotated, those diagonal lines become the horizontal rows of Pascal's triangle. Lovely stuff. Okay, so you've convinced me now, I think, that the binomial coefficients, which some people write like this as a vector kind of notation, and some people write 5 choice 2, you've convinced me that they're something to do with snails moving through the grid, which is then something to do with an addition rule, like in Pascal's triangle, and also those choosing things come up in the context of choosing things, which is the same as the snail. So all of these concepts are the same as each other. And something someone asked in chat, it's not obvious that these things are the same. If you tell enough stories that relate them together, they're all telling you things about the snail moving through the grid. I think it's really nice.
Yeah, no, it's one of my favourite things to do with binomial coefficients. So now I'm going to move on and I'm going to talk about another story proof, which is called Vandermonde's identity.
Okay.
I'm just going to get us to write down the formula. I think I sent you this because I don't think anyone wants to listen to me telling you this formula. I can.
Just open the file. A really prepared person would have had this up before. Yeah, here we go. Okay, it's a fact about binomial coefficients. I'd be really interested to know if chat already knows this. If chat already knows this, then wow, chat knows a lot about binomial coefficients. It's got a sum in it. So this is the sum that says add together lots of things for different values of k, where k is 0, 1, 2, 3, 4, all the way up to r, one of the variables on the left. The sum of products of binomial coefficients. Let's fix my handwriting a little bit there. So it says if you want m plus n choose r, then what you can do is take lots of binomial coefficients with m or n on the top, choosing different things, and multiply the pairs together, add them all up, and oh my goodness, you get the thing on the left. I'm really interested if people in chat already know this already know this identity. If not, that's great because we're going to prove it. Over to you, I think, Eve, unless I've suddenly been put on the spot to prove Vandermonde's identity. Oh yeah, let's wait for chat.
Yeah.
And there is a bias towards people who have seen things telling us that they've seen things. One of the advantages of having anonymous chat is that sometimes they tell us they haven't seen things. Andres will say. So, oh yeah, sure. So example, have you got numbers in mind, or shall I just pick random numbers?
I don't have numbers in mind.
Okay, I'll do 5 choose 2. So here's an example with. Do I want 5 choose 2?
Slightly bigger numbers.
I think I want slightly larger numbers to really get this going. Yeah, 2 is not a very large sum, is it? 7 choose 3?
That's probably, yeah.
That's probably good, isn't it? Where I'm imagining, I think m is 5 and n is 2 and r is 3. And I'm going to find out what happens. So this is the sum from k is 0 up to 3. I might expand the sum in a second, but just to give you an example, on the right, I need to put 5 here, I need to put 2 here, I need to put k here, I need to put 3 minus k here. Let's expand the sum just to make that more explicit. This says 2 choose 3, Eve. Have I messed up, or is that just a feature of this?
There's just no ways of doing that. So.
Oh, that's just 0. Okay, so we're imagining Pascal's triangle is kind of surrounded by zeros. Oh, wait, no, I actually prefer your phrase there, sorry. Shouldn't have talked over you again, sorry. There are no ways to choose 3 things if you only have 2 things.
Yeah.
Sorry, I always default to Pascal's triangle. That's the second time in half an hour that I've jumped at the opportunity to mention Pascal's triangle. How far am I going with this one? Oh yeah, I'm going to 3.
Yeah, I think drawing this out in Pascal's triangle is probably not great to do on the board. But if people want to maybe after look at some examples and what it tells you about where you're multiplying things together.
Right, so you could find these things in Pascal's triangle, circle all
Yeah,
of them,
because
think about patterns.
you've kind of got two rows of Pascal's triangle and you're sort of cross multiplying them.
Oh yeah, you're reading them in
Or
reading them in opposite directions,
yeah,
cross
multiplying
multiplying,
together.
like a sort of
So that gives
freaky.
you something lower down.
Yeah, that is not feeling like a helpful way to prove this or understand it.
No, it's not a helpful way to prove this, but it's quite a nice picture, and I think it's how I remember it.
Okay, you see that I bang on about Pascal's triangle too much, so we briefly considered doing this with Pascal's triangle, realised that would be horrible, and now I think you're going to tell me a story that explains why this is true.
I'm gonna get chat to think about ways we might go about a story.
Ooh.
So that the right hand side looks kind of messy. So figuring out what that might count. If we can figure out what it would count, it would probably be super helpful, but it might be quite difficult to figure out what it can count. So instead, let's try and figure out something that the left hand side counts. And the first thing that kind of comes to mind is saying, oh, well, it counts the number of ways of choosing R out of n plus n things. But the n plus n being added together and being kind of different from each other and splitting up on the other side tells us we might want to interpret that into the kind of the story of what's being counted here.
Okay.
So I'm not sure anyone will get this, but I want to give the opportunity to chat to think about something this might count.
Yeah, I guess we're asking chat to invent a situation where you might be to use my numbers, you might be inventing a situation where you're choosing 3 things from 7, but the 7 is kind of really 5 and 2. There's some essential 5 plus 2 nature to the 7 somehow. That's the thing we're doing out loud now is not the story. This is just all the maths and the numbers, and we're bogged down. A good story would be a situation where you want to do something like that, because then we could maybe engage with the situation, describe it in a different way, and get something looking like the right-hand side.
Exactly.
2 ways to count the same thing. Okay, let's see if chat can come up with a situation where you might have 5 plus 2 things and want to select 3. I'm going to think. Someone in chat says snail moving on a 4D grid. Yeah, okay. Let's just quickly imagine 4D snails. I think they're being funny about higher dimensions, but also, yeah.
I think if you wanted to extend the dimensions of the grid, you would be looking at something other than. You'd want to be choosing other things. You can do that, and it's interesting, but it's not the answer to this problem.
Callie in chat has posted in chat, which reminds me I should introduce Callie. Callie's moderating chat. You can say hi to Callie if you like, people in chat. Callie's a current student here, so also chatting to people in chat. Oh, I like this one. I like that one a lot. So someone's put, you've got 5 bananas and 2 apples, and you just need like 3 bits of fruit, doesn't really matter. Or 3 animals from 5 cats and 2 dogs. Anonymous says,
Right, yeah.
Weekends. You're trying to choose days in a week. 7 choose 3. But weekends come in 5 choose 2 kind of variety.
Okay, no, I like
that
this.
one the most.
Yeah, no, they're really good. It's more imaginative than when I was writing this talk. I was like, okay, about year 12. Year 12 has 16 and 17-year-olds in it. So I'm going to think about choosing some people to go to maths club from a year 12 class. And some of them are 17 and some of them are 16.
Are you up for improving this based on days of the week, based on how the numbers have fallen out randomly?
Could we go with pieces of fruit just because
Okay.
I don't want to be tied to the number 7?
Okay, fine. Yeah. Okay.
So I'll start with pieces of fruit, which is I think you have 5 bananas and 2 apples to start with. And certainly there are 7 choose 3 ways of choosing pieces of fruit when you have 5 apples and 2 bananas. But in some sense, I want to regard the bananas as different from each other and the apples as different from each other.
I see.
So
So which apples you're selecting and which bananas you're selecting, or
yeah,
the cats and dogs. The cats are kind of individual creatures that
yeah, maybe cats and dogs would have been better. Let's just
choosing
pretend that
apple.
I've written numbers on the bananas. So and then same on the apples. And I say I would like apple number 1 for my lunch, please.
I see. So the number of ways to select one apple is, the number of apples because they're all different and distinguishable to you.
Yeah, so that's gonna be important.
This is my second attempt at writing the word distinguishable. Nailed it. Okay.
Yeah, I can say there's definitely 7 choose 3 ways of choosing the fruit I'm eating for my lunch. I hope I'm eating something else as well, because that would be a weird lunch. How can I think about this in a way that will be like the 5 choose 0, 2 choose 3 plus 5 choose 1, 2 choose 2? I can say, well, the 5 choose 0 represents the way of not picking any of the bananas, right?
I'm gonna add in some numbers. I think you're doing this one.
And the 2 choose 3 would be the number of ways of picking 3 apples out of my 2.
Okay, so that's impossible.
It can't be done, but I'm interested in what it's representing, right? So that term is 0. But then I could move on and I could say, okay, well, 5 choose 1, that's the number of ways of choosing one banana out of my 5.
One banana and 2 apples. I see, but the apples are distinguishable. Wow, handwriting fail. The apples are distinguishable, so the number of ways choosing your apples, you got some apples to choose from. You've got to choose 2 of them. So we do need a choosing coefficient there. 2 choose 2.
Yeah.
Okay.
And then next term, I think everyone will be happy that represents the way of choosing 2 bananas out of the 5 and 1 apple out of the 2.
And then the last one is if you have an entirely banana themed lunch that's no apples at all. Okay.
But they're all, yeah.
So I see. So the right hand side is kind of breaking it down in cases based on, have I understood this? The cases of how many bananas form.
Yeah, the cases of how many of each thing in each case.
Sure.
I think for distinguishability reasons for the general case, we should switch to the cats and dogs. I should have recognized that was better before I started.
I think people have stronger feelings that cats are distinguishable versus apples.
Yeah.
Cats, people give names to and get cross if you permute them, whereas apples, people are less attached to apples.
Yeah. So.
Yeah. The weird sum is the complicated methods that you sometimes use for combinatorics problems, and then you find out that it's as easy as just doing 7 choose 3. You've maybe got this great idea about breaking it down into sub-cases and analysing each of them separately and then adding together all of your cases. That's this.
Yeah, but if only you had decided there weren't cases to start with and just done it, yeah. But then you can kind of take this frustration at the fact that you're often doing this and use it to prove an equality between a simple thing and a complicated thing, which is what's going on. So in general, if I've got an animal shelter with N dogs and N cats who have all got names and we know they're all different from each other, and although they're also still apples apparently, so if I've got these M dogs and these N cats and I'm interested in saying, okay, I want to what sports would cats and dogs play?
Sports with cats and dogs.
I want to form a team of R of them, but I don't know what my motivation is for forming.
Oh, you're forming a team, right?
Yeah.
Feels like the setup for a really good pun. I'm gonna think about that. But sure, you're building a team that's made up of cats and dogs, and then you've got choices about how many cats you field on your team and how many.
Yeah, so I'm like, I've definitely got M plus N choose R ways of forming a team of R animals from my shelter. And that can also be represented as the number of teams with no cats on and R dogs, 1 cat, and R minus 1 dogs, 2 cats and R minus 2 dogs, and so on, until all R of them are cats.
Right.
Which is my proof that those 2 things are the same as each other.
Yeah, that's your story about forming a heartwarming animal team possibilities. And in one sense, the story is just, well, you've got so many animals and you've got to put them on a team, so it's a simple choosing situation. And then because you can break it down into all these cases, I really do like that thing about the weird sum being the complicated way you sometimes try to do problems and then you realise there was a quick way. Pentathlon! You genius! Chat is a genius! We got it across the line. Perfect. I can't believe you've done that as an anonymous person rather than taking credit. Good. Okay. The thing that this reminds me of, when I see these sums going in different directions, so the numbers going up in one sense and down on the other one, that reminds me of polynomial multiplication. And like you do the x cubed times the constant, you do the x squared times the x, you do the x times the x squared, you do the constant times the x cubed. And that's, I think, not a coincidence. And I might leave that for chat to think about.
Yeah, I think that's a good one to leave.
It's not a coincidence. Okay, complicated identity status proved by pentathlon. Right, have we got another one? We've got 10-15 minutes on the clock.
Yeah, I think I'll move away from binomial coefficients because I don't want to give the impression that you can only prove things about binomial coefficients using this method. It's actually a really good method for loads of things. I use it in my research, so like definitely still current, still important. Should we prove there's infinitely many primes?
Seems like a good idea. I mean, people maybe already know that there are infinitely many primes, and people maybe know a proof that there are infinitely many primes, but
they maybe already know this proof, but I'm not convinced that they will. So Erdős found a proof that there are infinitely many primes that kind of involves counting the numbers you can make given some finite set of prime numbers, and then saying, well, I don't have enough numbers, you must have missed some primes.
I see, okay. So you're going to suppose there are finitely many primes and try and use those to build, like building blocks to build all of the numbers.
Yeah. And the way Erdős did that was to look at like whether or not numbers have square factors, and then to argue about the size of numbers based on their square factors. So he always said, okay, suppose I've got finitely many primes. I've got P1, P2, up to Pk.
Okay, I'll write that. This is proof by contradiction, right? So you're imagining that there are finitely many primes, P1, P2, P3, but then crucially this list stops.
Yeah.
How many did you say? Pk?
Pk, useful. Okay. Super important. So far it looks like Euclid's proof that people are more likely to have seen. But now we depart from that. So let's take some number n. And n can then be written as some square number. M squared, that's what I wrote, so I'm really glad you chose that notation. Times some kind of factors P1 to some power, but not high power. Yeah, let's go with that. Same with P2. And all the way down.
Okay. So hang on, let me think. If the number n really has a factor of P1 to the power of 5 or something, then I can think of some of that being square number and a leftover.
Yeah, you think of the 4 as being bundled into the P1 squared, so that would be counting in the n.
Well, it's a bit much with the subscripts and the superscripts. Sorry, this is P1 to the power of 5. I'm sort of trying to imagine that that's P1 squared times P1. Okay, so you bundle this up as part of m squared. Put that in m squared.
P1 squared would be part of m, definitely.
I see. Okay, so you bundle those all together.
Yeah. So these powers, these alpha 1, alpha 2, and so on, are all 0 or 1.
Okay. Each of them. I can't be bothered to write alpha 1, alpha 2, alpha 3 again. I'll put alpha right. Okay, they're all 0 or 1.
Yeah, so we can get some kind of rough bounds on the number of numbers we've got that are less than or equal to n. So n, the number n definitely counts the number of numbers in the set 1, 2, and so on up to n, right? That's easy.
Okay, this is the counting problem where you say, how many numbers are in the set 1 up to n? And it's the easiest counting problem ever because the numbers are already numbered. The answer is n.
So the answer is n.
Okay.
And I'm now going to try and write each of them out in this kind of square form times some primes.
Okay.
So I definitely have my little m has got to be less than or equal to the square root of n, right?
Yeah, I suppose the square bit can't be bigger than the number, so m squared has got to be... Oh, right, hang on. What do I need to write here? I need to write m is less than or equal to the square root of n?
Square root of n.
Yeah, I got my squares mixed up. And I realised by talking about it out loud, story proof. Yeah, m squared is the largest square factor of n. I like that a lot. Thank you, Anonymous. Yeah, and the largest square factor of m can't be bigger than n, so yeah, good. Okay, sorry, carry on.
So m is at most root n, and then you've got these kind of prime things, and you can say, okay, I've got at most root n choices for the number that I square.
Mm-hmm.
And how many choices do I have for the tail bit? How many choices do I have for p1 to the alpha 1, p2 to the alpha 2, and so on, pk up to the alpha k?
So 2 choices for this one because it's either 0 or 1. I think after you've pulled out the biggest square factor, this is 0, 1.
Yeah.
This one is also 0, 1. Chat's probably ahead of me. Chat's often ahead of me. So I've got lots of separate choices. It's not binomial coefficients, but it is still choosing things. I think this is 2 to the power of k, different like tail bits. It's more complicated to write them with all these primes, but each one is either there or it's not after you've taken out the square factor. It's not there twice, that's more square. So, okay, 2 to the k choices for what I put over there.
Yeah.
I don't really know k. Okay.
So there are at most 2 to the k times root n different numbers that you can write using this.
Oh, okay, so we're imagining writing everything up to n.
Yeah,
to
all
some
of the
n, up
numbers
to
in
n.
that length number, not just n itself.
Oh, I'm glad you haven't maybe write that on the board, but we're imagining writing all of the numbers 2, 3, 4, maybe 2's on our list that's prime, 3, maybe 3's on our list that's prime, or maybe 4, okay, maybe 4 you write out all m squared. It's one of our examples of a small number m. Okay, right, you've got to write out all of them, and obviously the things on the right should be different. There are at most 2 to the k root n of them.
Exactly, okay. Yeah. And so we must have, if we've got kind of every number can be written out in this way, that has got to be at least as big as n.
Oh, no. Okay, I kind of see where this is going. We need 2 to the k, so it's a huge possibility for whether you have primes there or not, times root n to be bigger than or equal to n to write out each number.
Yeah, and that's going to cause you some problems, because if we can rearrange this to, you need k to be at least log 2 of root n. I've done that in my head and now lost all faith that I've done it properly.
Well, k's fixed, right? So
k's fixed, yeah.
K's fixed, so eventually this root n thing is just not as large as
exactly.
N. This thing slows down, right? Root n looks like this. It might have a huge coefficient on it, 2 to the k. But eventually, this boring old n on the right-hand side is going to catch up and overtake. Desmos challenge, please plot root n times a large number and just n. You'll see that n catches up over again. Chat, what's the last bit again? M can be 1, yes. If the number is just made of random primes, or if it is the number 1, then there's no square factor in there other than the number 1. Chat wants the last bit again, which I think is, and also wants to know whether n is equal to m squared, and I think that's not quite, because...
Sorry, which bit does it want again? I'm slightly confused.
Yeah, so I think I'm going to have a go at doing the bit that was light bulb for me, because that's how I do it. So I said the light bulb bit for me. The suggestion is that we write each of the numbers 1 up to n. Mm-hmm. Let me drag all of this down, or more easily drag all of this up. Right, okay, suppose you've only got finite many primes. then you should be able to write all of the numbers 1 to n, all the numbers 1 to n in this format on the right hand side. Now I don't know what your primes are, so I can't literally write that out. I think this is going to be m is 1 in the first case and all of the powers are 0. Okay, fine, I lied, I can factorise 1. Even my powers of number theory, I'm able to factorise the number 1. And then 2, it kind of depends if 2's in your list or not, so I'll be vague. 2 should probably be in your list, it is definitely prime, but that's not part of the proof. And the proof says you're going to write all of these in this kind of this format, where m, I guess m is different for each number, so technically I should give all the m's slightly different letters or subscripts or something, I can't be bothered, but you sort of write them in this format. All of the lines are supposed to be different. Let's count how many different things can appear on the right hand side. It's not that many, because the number m, the kind of square factor that appears here, not very many possibilities for that. And the primes only appear to powers of 0, 1. There are quite a lot of possibilities, because you've got this grid of like 0s and 1s and binary sequences. Quite a lot of possibilities. 2 to the k possibilities, that's loads. It feels like the right hand side, there's loads of things that could be on the right hand side. 2 to the k times root n. But then you think about it, and you realise that 2 to the k root n is not that big.
Yeah, in particular, when n gets larger than 2 to the power of 2k, this is going to be a problem.
Okay. Problem. If you've done the inequality, thank you. What is it? 4 to the k? 2 to the k?
My root is 2 to the 2k, I think,
yeah,
right now.
Okay, because then the square root is 2 to k and then it's bigger, okay. So if n gets too large, if we're trying to make it greedy, like all of the numbers up to 1 billion using this format, there's just not enough factorizations to go round. That's mad.
So yeah, you run out of numbers that you can make this way.
Yeah, so this root n, just one more time, sorry, this root n is because of the possibilities for what the square bit could be. I've put the number m in every line. I shouldn't really have done that. This should be like m1, m2, m3 up to mn for like these things where it's like all of the different square factors here. There's a bound on how big the square factors could be. I should write, they're different numbers in each row, but there's a limit to how large they can be, and they're whole numbers. So there's root n possibilities for what this term is. Root n. Oh gosh. Enunciate. Okay. Huh. That's kind of nice. It takes a long time to go wrong, because 2 to the 2k is big. If I name 10 primes, then Erdős proves that I have a problem when I get to the number 1 million, more or less, I think.
Yeah.
But actually I have problems way before that.
You will have problems significantly in advance of this, so...
Yeah, when I hit the 11th prime. But that's really nice. 2 ways of counting.
It's a lot better than the bound that Euclid's proof gives you.
Yeah, because Euclid says something like, multiply all of them together, right?
Multiply everything together, and that, you know, it's a lovely proof, but the bound is...
this proves that there's another prime... does it prove there's another prime below 4 to the k? I mean, that's still ridiculous bound, but...
Yeah, I'm not completely sure. That one is constructive, though. It tells you kind of a number that you can find. If you can factorize a number, then you can find a prime that isn't in your list.
Yeah.
This one,
so this one, the problem falling at 4 to the k, I guess it could be the case that, annoyingly, it was the next number. The point where it fails is immediately when we find a prime, so it might be the case that the next prime is only at 4 to the k. I mean, that's just not true, but it's kind of worst case analysis, I think. Yeah. Don't try to do number theory live. Right. Okay, I like this proof a lot. This is very good. Someone's mentioned that it did come on it's on the Sunday stream, which is a separate live stream that does more number theory.
Oh.
Cool. Somebody else is asking where the 2 to the k comes from, and that's to do with the non-square factors. There's not, you don't get much choice of what these powers are if you've pulled out all of the square factor, just normal one.
Yeah, you've got to choose either of them to be either 0 or 1. So there's 2 choices for each one, and there's k of them. So you're multiplying 2 with itself k times.
Okay. So there was a bit of a plan to talk about partitions of numbers and splitting things down and doing other stories. I think we're running out of time.
Yeah, I think we're going to struggle to fit that in.
I think we're going to struggle to fit that in before 6 o'clock. Maybe we could mention some of it in the further reading notes or
Yeah,
point
no,
people
I've,
towards.
there's a really nice proof that I will put in there, which I actually prefer if people can read it because I don't want to ruin it before they have chance.
Yeah, okay, let's not rush it. Let's type up a version for further reading notes. Further reading appears on the Maths Club website, which I'm going to point to down there on the screen, at maths.ox.act.uk/r/club. That's where you can find about 70 or 80 previous episodes of the Oxford Online Maths Club, and get links to things like Jane Street and other resources, other fun that maths is up to. The Sunday stream that Neutrino is talking about in chat is my personal stream, so if you want to see more of me, you can subscribe to my unprofessional stream on Sundays on Twitch. I'm quite easy to find. There's not very many people streaming mathematics on Sundays on Twitch. Eve, if people want to find more of your work or what you're up to, is there anything you want to point to?
Beyond Step Summer School, at the minute, I've not got anything live.
Good excuse to plug this.
I'm going to use this as an excellent excuse to plug my Step Summer School.
Cool. Okay. We will be back in 167 hours for another episode of the Oxford Online Maths Club. But until then, have a lovely evening and a lovely week. Eve, thank you very much for coming on the stream and showing us proof by story. Once upon a time, there was some maths. Thank you very much. We'll see you around. And I guess we have to end by saying they all lived happily ever after.
You do it, yeah.
Great. Okay. Take care, everyone. See you next week. Bye.
Okay.